Good evening, everyone. My name is Tulsi Bisain, and today I will be presenting this presentation on activation functions. So first, we will see what are the activation functions and what is the importance of activation function in the deep learning networks. So first, we will see what is activation function. So activation function is it is a triggering agent, and it is like a triggering agent for the graph of the deep neural network. Okay, and it also it takes the input of the neural network and it activates the neurons based on the input functions, and the weights are calculated, and this output will be passed to the another neurons. So activation function is responsible that which neuron has to be activated or not. So, and this also introduces the non-linearity into the output of the neuron. Non-linearity means when our problems are very simple, then we can use the linear functions to solve it. But when our problems gets more complicated, then we have to process them in the non-linear manner, and so in that way we have to solve their problems if they are little bit in the complex side. Okay, so therefore the activation functions are very useful in this type of problems, and therefore it is the backbone of the neural networks. So why we need non-linearity? Because I have already explained you that without activation function, our neural network will be acting like as a linear regression model. So we can use very simple problems. We can solve very simple problems with that. Now you can see here, these are the inputs to the networks. Okay, and here we are. These are the weights related to every input, associated with every input, and now we are summing this x into w1, x2 into w2, x3 into w3, and so on. Whatever are there are inputs available to us for the network, and then we are adding bias also if required, and then this summation of the wixi and the bias, and this will pass to the activation function. Now this activation function is triggering the neurons, whatever the neurons activations are required. So according to that, this calculation is passed to the next neuron for the further calculation. So activation function is used in each hidden layer neurons presented. So this will show as the one neuron for the hidden layers. Okay, so this is the activation function associated with each neuron. So this is the formula to calculate the output. Why is the output? Activation function worked on the weight and the input and the bias. Okay. Next is so we have to use activation function necessarily or not. So this we have already discussed that without activation function, a network will be worked as a linear function. So to solve complex problem, we have to use activation functions. Okay, now we will see the different type of activations functions. So first is binary step function. So in binary step function, if there we are fixing our threshold. Okay, so if the input is below the threshold, the neuron will not be activated. If it is above the threshold, then the neuron will be activated and output will be generated. So here we can see that suppose our and okay, what the main function of the neural networks is we are calculating the errors. Okay, and according to the errors, we are back propagating the networks. There we are adjusting the weights and the bias according to our required output. So when we are doing feed forwarding, means we are simply passing our input. But when we are back propagating to calculate and to resolve the error, so we have to back propagate into the network, and that is where we have to derivate our function. Okay, so in that case, in the duration of the back propagation, we have to calculate f dash x. So the function, how it is functioning when we are back propagating, means when we are getting when we are deriving the function. That is the main purpose here to explain. So we have to calculate the derivation of this function also. First derivative we have to calculate, that will be used as the error calculation. Okay, or that is the process when we are back propagating the network. So fx is equal to 1. So this is the threshold, means when x is greater than 0. 0 is our threshold. If x is greater than, here we can see in the graph, if x is less than 0, the graph will not be activated. The neuron will not be activated. If it is greater than 0, 0 means here in the x line, if it will be greater than 0, the activation function will be will activate the neuron. So in this way we will get the output. Now what happened when we are back propagating this? So we have to calculate the first derivative of this function. So f dash x. So what will be the f dash x of 1? It will be 0. Okay, Deep, you can interact at this time. Okay, you can also talk. So here in f dash x, the derivative of 1 is the constant value, so therefore the derivative will be 0. So how can the graph will look like now? Just 1 minute. The graph will look like now the constant means the we will get the output like this. Okay, so in every iteration we will get the same output. So that will be the problem with this binary step function. This is also called a step function. Okay, so this will be the problem with this. We can solve the binary related problem, means 0 or 1 kind of problem with this activation function. Now next will be linear function. So linear function, it can be solved. The linear function can be solved, linear type of problem, very simple problems. And and we will calculate, this is the formula for the linear function. A is the constant. So when we are differentiating this with respect to x, we will get f dash x is equal to a. A means whatever is the constant value here. So you can see here the red line. You can see here the red line. So this red line is showing the derivative value. Okay, so we will get the constant value here. You can see. Okay, sorry, in the previous graph I have drawn this line. So this line, this here, so this will not be here, sorry for that. Okay, this will be like on the 0 0, we are getting 0 now, so that will be the on the 0. So this will be the graph after derivation. And sorry for that. And in the linear function, which we are getting this line. Okay, for this is the constant. Here fx is equal to 4x, therefore we are getting constant line on the 4. So it will generate only one single output every time. So that is the problem with linear function. So we this linear function can solve linear problems, but complex problem cannot solve by it. So therefore we will move ahead with a different type of activation function. Next is sigmoid function. So sigmoid function is non-linear activation functions. This is like a smooth S type of curve, but here the activation function is activated on the value 0.5. You can see here 0.5, and this is the formula for active sigmoid function is 1 by 1 plus e to the power minus z. So here z is the weight and the input, x into the input plus bias. So this will be the z here. And when we are when we are you can see here the graph. This orange one is the graph after derivation, when we are getting derivative. So you can see here the value will be the top of the curve, that will be 0.25. Okay, the orange one. So this is the range 0 to 0.25 after derivation. So this way this range will be covered by this function. Okay, so this sigmoid function is used widely because it gives the output between 0 to 1. You can see here in the graph, that is 0 to 1. So this type of these problems can be solved here. So if it is 0 and then it is smoothly going on up the upside, and after 0 0.5 the neurons will highly activated in that part. Okay, and because we are getting 0 to 1 means in the problems we are where the probability calculations are mainly done, so sigmoid will be very useful in that type of problems. Now next is tan h. So tan hyperbolic function. So this is similar to the sigmoid function that you can see here, but the graph, our sigmoid function is our sigmoid function is activated here. Okay, our sigmoid function is activated from here, from 0 0.5, and our tan h function will be activated from 0. So this is the graph, and after derivative, after getting the derivation, our graph will be look like this. Okay, so the value of the graph will be ranging from 0 to 1. So it will cover maximum of the values, and uh, our that in the sigmoid function we were getting, just 1 minute, we were getting this type of curve. Okay, this type of curve, this value was 0.25. This value was 0.25. So the tan h covers high range of the value 0 to 1. Okay, and sigmoid was covering 0 to 0.25. So that was the difference between sigmoid and the this function, tan h function. Now next, so this is preferred over sigmoid function because we have already seen that after derivative of this function, we are we are covering the high range from the by 10h activation function. Okay, derivative means the gradient which we have calculated. Gradient means how we are calculating the how we are reducing our error, so that is called the gradient. But there are some problems which is related to sigmoid and tan h function, that is vanishing gradient problem. Because we are doing it in the back propagation network, in order to reduce the loss function, we are doing back propagation. Okay, so gradient of sigmoid ranges from 0 to 2.5 and tan h ranges from 0 to 1. So if we are going to each layer, the gradient is that steadily it is reducing and going getting smaller and smaller. Okay, so because of these smaller values, it will at some point it will be equivalent to 0. So therefore equivalent to 0 means it will give no output. Okay, it is not learning anything. The our network is not learning anything. It get just idle. Okay, so therefore that is the problem of vanishing gradient problem associated with this sigmoid function and tan h functions. So after that, we are using the ReLU function to overcome all the problems. It is taking the values from 0 to x. Okay, the function will be 0 to x. If x is less than 0, it will give us 0, and if x is greater than 0, it will give us 0. So this is the sigmoid function without derivative. So here we can see that after the values below 0, it is giving us the 0, means the function is not activating any neurons here, but after 0 the function will be will get activated, function will activate some neurons here. So this is the ReLU after derivative function. So here the you can see here 0 to x. So for 0 it is not giving any output, for x it will give a constant output. Okay, so because here function is ax, a is value is 1, so here we are constantly getting a constant value after derivative of getting the derivative of the function. So it will give a constant value, and there are some problem associated with ReLU is that because of this 0 value, if there are some values which resides in this part also, it will constantly give 0, means whatever weights we are getting for this this region, okay, whatever weights we are getting in this region, the weights are nullified, the weights become 0, because it are these are multiplying with the input values. So here input values are 0, so weights also become 0. So the weights which we are passing in further processing, that are already 0, but actually they are not 0. Okay, but actually they are not 0, so that is a problem with the ReLU. So and that is called dying ReLU also. This problem is known as the dying ReLU problem. So after in tomorrow's session we will see the other activation functions also, and what can we do, the problem associated with the ReLU function. So this all are the today's topic. We have seen here the binary activation function, okay, the linear activation function, the sigmoid function, tanh function, and ReLU function. Okay, so we will continue this in the next class. So if there is any query, then you can ask here.
No, Tulsi, it was very good presentation.
Okay. Okay, thank you, Deep.